Okay, so this is Lab 6A mutation on evolutionary computing subject. So we are still solving the knapsack problem. You should remember this by now. We have 8 items. We want to select the best item to fill in the bag so that the total weight is as close as capacity. So up until last week, we have done up until crossover. Okay, this is our algorithm design, and now we want to continue with mutation. Mutation lab is pretty straightforward. It more or less like crossover. So let's recap what is mutation first. What do you understand about mutation, Arif? Arif, mic okay?
Hello.
Hello, yes.
Mutation is something to do with the changes in the chromosome, either in crossover or in a combination or anything lah.
Okay, changes in chromosome correct. Tapi but crossover is crossover, mutation is mutation. So crossover is changing the chromosome as well. Mutation also changing the chromosome. So what is the difference between crossover and mutation? Melvin? Oh, Melvin tak boleh cakap ya. Okay, sorry. Wong.
Yes.
What is the difference between crossover and mutation? What do you think?
Crossover dia guna parent
Betul.
macam dua
Okay,
chromosome.
two chromosome. And mutation?
So dia mutation dia hanya guna macam children saja.
Guna children saja. Guna one chromosome only lah if you want to compare like that. Crossover needs to input two chromosome. That's crossover. Mutation just needs one. Both crossover and mutation will produce a new children. Okay, what is the difference apart from the input? Two chromosome versus one chromosome. What else? Tungnan, try. Tungnan, are you there?
Doctor, I was away just now.
Apa?
I was away just now.
Okay. Jensen, try.
Can Doctor hear me?
Yes.
So from my understanding is crossover is to create changes within the population, and mutation is to, how should I say, create random changes that are to introduce the random changes into the population that are not exist in the population itself.
Betul, correct. So crossover is something that already in the family. It's inherited from the parents. Mutation is something from outside. Okay, random value from outside. We purposely introduce mutation in the case of the family is not good enough. The inherit gene is not good enough. So we introduce mutation so that mutation maybe can make our chromosome or our solution jump out from local solution. Okay, so both create new chromosome crossover based on whatever we have in the family or in the current population. Mutation is something from outside. Okay, but we don't want mutation to be. Usually, we want mutation to have a lower operation compared to crossover. Okay, we'll discuss about this again later. Okay, that's mutation. So there are a few strategies on mutation. One of them is listed there, bit flip mutation. What is other mutation strategy that you can remember? Syamhini Devi, ingat tak?
Doctor?
Yes. Do you still remember any mutation strategy that we have learned in class?
Bit flip.
Bit flip, yes. How does that process goes? Bit flip?
And change the value into the opposite value. If there
Yes.
is 0 and change into 1.
Okay, that's what we're going to do today. Any other crossover strategy? Hussein, ingat tak Hussein? Hussein? Not sure. Okay. Tang? Tang ni ramai dalam kelas saya rasa ada 4 tang ni. Which tang ni? Tang, are you there? Can you type or speak up? Okay. Do you still remember any mutation strategy that we have learned in class?
Sub and insert mutation.
Sorry?
Sub and insert mutation.
Yes, swap insert mutation is for permutation chromosome, but it is mutation strategy. You have insert, swap, scramble, inversion, mutation. For non-permutation, you have bit flip, floating point mutation, and integer. It's like bit flip, but for integer representation. Okay. So we are going to do the mutation today. That is the pseudocode. Let's start with our code. Everybody has the code up until crossover. I think most of you are in my class last time. Okay. I hope you have. Up until crossover. I'm sharing my IDE now for the coding. Okay, can you see the coding?
Yes.
By the way, what is your view? What is your view there? Because when I record, I noticed that apart from my screen, there is like apa tu? The grid of participants up above the screen that I'm sharing. Did you view that as well?
Yes. There's a list. I mean, like names up there.
Or is it because I already closed that in my end? Is that your end or is it default view? I mean, like if I record it, it still be appear.
Today is different already.
See the view. Yeah.
Okay, so we cannot do anything about it. Okay, so up until last week, let's start from above. We have introduced these two data structure. Okay, parents and children. And then we have the constant variable for crossover probability as well. And we have this function initialized population, print chromosome, aggregate chromosome. We have up until before the MCO. Last week we do parent selection and crossover. So this is all the function you have. Now let's start with mutation. Okay, first, mutation same like crossover. It also has probability. This indicate whether we want how frequent we want mutation to happen. Okay, so first, declare constant similar like crossover probability, but let's rename it as mutation probability. Let's set it high first, but usually we set this very low. I set it 0.9 first, so I can see the code happening. Okay. Do you still remember what this is for? Mute probability. Tungnan tadi tak jawab kan? Ni line 12 ni. What is this for?
It's probability for mutation. So we don't want mutation for everything. We just want like randomly if it happens.
Okay, so if I put the value of 0.9. What does this mean?
It has a 90% probability of mutation.
Okay, good, correct. So that is how you control the mutation process in your code. Okay, that's one. And then we don't need any new data structure. We will mutate whatever result from the crossover. So the result from crossover is stored in children data structure. So we will change whatever in children data structure for mutation. I'm sharing my PowerPoint to show you the data structure that we have. Okay, so we have, can you see?
Yeah.
Okay. So we have the chromosome fitness. This is previous lab. Last week we have parent as well as children. So the children is result of the crossover operation from parents. Now the children itself, we want to change this and do the mutation. Okay. Okay. So next one is to add another function. Let's do it after crossover. Void mutation. Let it blank first. And then don't forget to call the mutation from main. So I just copy this one. Now it's crossover mutation function and call mutation. So we have, what I have added is mutation function and function call. Okay, everybody follow?
Yeah.
Okay. Arif, okay?
Sekejap, tengah salin.
Sudden type
Yeah.
Okay, saya tambah what I heard just now is line 12. Okay, this indicate how frequent will mutation happen. And then no new global declaration. We will work with whatever we have in children. New function for mutation, line 1 to 6 and 1 to 7, empty function first and function call. Okay, and function call. Husin done? Shamini Devi, okay?
Done.
Okay, good. Okay, let's continue. So for mutation, let's look at the pseudocode first. Okay, here is my slide. You can see the pseudocode here. So now we have children. Okay, we have children. We have two children. This is what we're going to mutate. It might be the new children resulted from the crossover. It might be the parents that you have copied to children. So we want to consider these two chromosomes, whether we want to mutate the genes or not. So the process is for both children, we will generate a number, and this number will be compared with mutation probability. If it is less than probability, then mutation will happen. Mutation is the 3.2 process. Okay, generate mutation bit, print the mutation bit and flip the gene. Okay. Otherwise, we leave it as it is. Mutation don't happen. Okay, now for both children, we start with 4 and we start with generating a number to know whether the mutation happen or not happen. Okay, let's declare the variable first. This is probability, mutation probability. So for both children, okay, for both children, we need to generate a random number. So let's declare the random number up here. Oh, that is the probability, sorry. We have declared it as probability. So probability equal to, okay, we're going to generate a random number here. From what number to what number? This is to 0 to 1. Okay, how are we going to do that? What is the code again?
Random, ran,
Ran, and then modulus with what?
modulus with
1.
10.
2? Apa tu? At the
10.
Plus 10 plus 1.
10 plus 1 and then divide by 10.
Okay, last time we did 10 plus 1 kan? So, is there any
It should.
difference if I put straight away 11 here?
11 means the range would be from 0 to 1. If we do 10 plus 1, then the range would be from 1 to 10 instead of 0 to 10, right?
Okay, come again. Let's check. If I do rand it modulus 11, the rand only will give me 0 to 10, correct?
0 to 10, yes.
10 to 10. So I divide by 10, it becomes 0 to 1.
1.
Okay. Comparing with what we did in crossover here. Crossover here, crossover this one. Last time I plus 1, correct?
Yeah.
It's missing now. Okay, last time we do something like this. Okay, so what's the difference here? This statement give me 0 to 9 plus 1, I will get 1 to 10.
10.
So the difference is the first value, right?
Yes.
0 and 1. So do we need the 0?
Yes, yes.
So it's better if we modulus it at 11, right?
Yeah.
Okay, so let's stick to this one, okay? You can check it back later. This one works, but you might missing some value. Although it's not really a serious logic error, but you might still want to consider that. This is one way. I just want to change it to random 11 just for mutation. So we get from 0 to 10 and we divide it with the floating point of 10. So we get 0 to 1 in decimal point. This is generating the probability value. Okay. Can you understand this part? Line 131?
Yeah.
Okay, how about everybody else? Kunan is okay.
Yeah, good.
Okay. Haziq okay? Arif okay? Not sure, Doctor. Okay, yeah, there is one.
Okay.
Okay, alright. Siapa tu? Arif ke?
Ya, saya.
Okay, memang suara baru bangun tidur. Okay, so this is just generating the probability value, and then after we get the probability value, we compare it with, dia compare dengan apa?
Mu probability, if probability less than mu probability.
Yes, a mute probability. So if probability less than mute probability, what will happen?
Mutation.
Mutation will happen. Okay, so let's look at the mutation process first. Okay, mutation, we going to do the bit flip mutation. So we are at our children 1 now. Okay, we are at children 1 now. We are at children 1 now. So let's say mutation will happen at children 1. What is the next step? What is the next step? What should we decide? We know that mutation will happen now. So what is the next step?
Which bit?
Which bit it will happen? Which gene it will happen? how do we decide which gene will get mutated?
Random.
A random number
Yes, random. So that's
modulo gene plus 1.
so we need to have mutation point. So I put here mute point. Okay, in crossover we have crossover point where we decide to cut the chromosome. In mutation we have mutation point. This is where the mutation will happen. This is referring to a particular gene. Okay, question. Can we have more than one gene mutate?
Yes.
Can.
Okay, it depends on algorithm designer, especially if you have long chromosome, maybe you have 50 genes ke, 100 genes ke. If you change only one gene, it doesn't help much. Okay, but at this stage, since we have 8 genes je, we just have one mutation point. Okay, so first generate the mutation point. Random from where? What?
Random modulo gene size plus 1.
Yes, gene. Okay, gene. So gene we have 8, so it will give us from 0 to 7. And then let's say this mutation point give us gene 3. Okay, gene 3. So gene 3 right now is 1. Okay, it is 1. So we need to change it to 0. Okay, that's what we're going to do in here. So if what data structure that hold our chromosome now?
Children.
Children of what index?
C.
C. And what genes that we are considering now?
Random point.
Random point.
Moot point. Yeah.
Mute point. So we already generate the mute point just now. So the gene at mute point. Okay, so the one that we consider is children here, children 1. Okay, children 1. And we have generated mute point, let's say mute point 3 just now. So we are considering mute point punya gene. If this gene equal to 0, let's say, then you will change it to
1.
1.
Doctor, won't it be more efficient that we straight away put as children C mute point equals to not point?
Boleh. Kalau if in this case it works if you have binary value.
Tak ya coding.
Saya punya coding. Kenapa? Siapa tu? Arif kan?
Arif, dia tak nampak macam dia keluar daripada kotak if tu ke? Yang equals to.
This one line 135
The equals to 0 tu dia keluar daripada kotak if.
Equal to 0 ni, children start here. Okay, ni ke? Okay. Tungnan, okay ke tadi saya jawab?
Yeah.
That's you. Okay, good. Okay, so children see, okay, thank you Haziq, saya ada extra bracket tadi. Children see midpoint, if it's equal to 0, then we assign it to 1. Else, indent tak betul. Okay, let's try first. Else, we change it to 0. Okay, this is just a bit flip. Okay, so if what happened here, if your children currently equal to 0, then you change it into 1. Else, if it's 1, we change it into 0. Okay, so this is the block that do the mutation part. Okay, everyone follow?
Yeah.
Okay, good. So how do we know this one work or not? As usual, we have to see out something to know whether this is actually working or not. It's more or less same like whatever we did in our chromosome. So I just copy. Okay. In your chromosome, crossover function, this is the line. Before you close the function, this is the line where you print the children. So I just copy and paste it after you end the for. This is end of for. So after we did the mutation, we want to print the children. So children 1 after mutation. Okay. If you don't have this code, you can, if you have different code or you didn't print it last time, you can type the new one here. Okay, other than this one, I also want to see at what gene the crossover get mutated. So I want to print the mutation point as well. So it's the same as we print the crossover point. We do it after we get the random point generated. Mutation at gene mute point. Okay, what else can be added here to improve the readability of the code? Any suggestion?
Doctor, I have a suggestion regarding on the code efficiency. So is it more efficient that we declare the mute point within the for loop, the if probability less than mute probability, so that we can, it does not generate for up there the mute point?
If you put it under for, if it happen, it will create two new two new variables every time. Instead of replacing.
What I mean is to shift line 128 to below 132.
128 below. Okay, I understand. Declaration happen inside for, correct?
Yeah, within the if loop.
Okay,
Within the if.
Okay, if both chromosome we do the mutation, you will have two variable. Okay, you will have two variable created. That is just for one mutation process. If you have another mutation process, you have another two. By doing outside for, we will have one variable only, regardless we use it or not. We only have one variable only. If you put it inside for, it will be how many chromosome get mutated. That is the number of mute point variable that you will create. If it's happened, let's say your chromosome, let's say your process, this mutation process will be repeated 100 times, and 50% out of the 100 times, you will do the mutation. So you have 50 variables of mute point. Okay. Compared to if you put outside the for, you only will have one, and will be replaced the value every time.
Oh, okay.
Okay, Ashraf want to say something just now?
No.
Tak ada. Okay, we more or less has completed the code, but what else can we see out just to increase the understanding of this code? Any other suggestion apart from Tungan just now?
The children after mutation.
Children mutation we already see out it here.
Before dah ada kat atas.
Before before we can see it here
Yeah, because it's up there.
because it continuous. Ni ha. Oh, I don't put it here. We want to know whether it happened or not happened. Okay, the mutation. So here, if in this case, if it happened, else if it did not happen, we just want to state mutation did not happen. So we should expect the same children as before. So here mutation did not happen. Okay. So this is if it happened, else it's not happen. So if this you see this, you need to check your children here won't change from crossover last time. Okay. Okay, so let's check whether this code working or not. Compile. Okay, no error. Initialization evaluate chromosome. This is parent selection for last time. So this is the parents. Okay. Crossover. My code is not very nice. The header, the function header is here mutation. So yeah.
Grey.
Okay, sorry. Okay, wait. I want to correct my output first. So here is /n/t. Okay. Compile it again. No error. I run. Hold on.
Doctor can't see your result.
Wait. I haven't shared it yet. I want to. My antivirus keep checking the output first. So let it done. Okay, now I'm sharing my screen. Okay. Now you can see my black screen.
Yeah.
Okay. So we up until parent selection, we do the crossover. Now this is the mutation. So both children, we did the mutation both at gene 3. Okay, gene 3. So this is the original. From the crossover function, this is the original children. Mutation at gene 3, so it's the fourth digit, 0, 1, 2, 3. It's 0, 1, 2, 3. It's changed, right? 0, 1, 2, 3. It's from 0 to 1. Okay, the second gene also the fourth digit. So the fourth digit is 0 to 1. Okay, so the code is correct in terms of executing the bit flip mutation. Okay, how about your code? How about your output?
My code said I have a missing semicolon, but I don't know where.
Okay. I'm finished. If everybody have already copy my code, then I can see your code. Siapa tadi? Arif ke Haziq?
Arif, but wait, jap.
Okay. Um.
Uh,
So anybody still want to refer to my code? Ashraf, okay?
Okay, okay.
Okay, Haziq. Haziq dapat? Dapat. Jensen? Tungnan?
Yeah. Okay.
Melvin and Hussein? Melvin okay. Hussein okay. Shamini Devi okay. Hussein okay. Shamini Devi, Tang Wong. Cepat sikit kan, boleh sentence seorang. Wong okay. Tang okay. Shamini Devi?
Okay, doctor.
Okay, good. Arif je. Arif, choose that have that error. You want to share your screen?
Dah doktor. Dah siap dah.
Okay, good. Okay, mutation simple je. That is about it. Okay, since we are using the simple mutation strategy as well, but it's related with crossover where we do the mutation on the children. Okay, that's one. And then, okay, now usually we don't have this high probability. Okay, we don't have this high probability. Usually, common value is 0.1. We only want to have 10% of destruction of our population. The population need to evolve based on whatever it has, whatever their ancestor have. So the mutation probability we usually set to 0.1. If it's too much, what do you think? Why don't we set it as high as 0.9? Kenapa? Why we want to keep it as low as possible?
Because later on we cannot focus.
Because what?
Because if later on when we want to refine the results, it cannot converge.
Cannot convert. What do you mean by cannot convert?
Everything it has a 90% of a mutation, right? Then it's difficult for us to narrow down. Once we want to narrow down and mutate again.
Narrow down apa yang tu lain saya tak dapat. And your voice is breaking a bit.
Sorry. Okay, so basically, like, let's say if you want to narrow down our results, like, let's say we want to generate a phrase. So when we want to narrow down to make it closer to our phrase, right, it will mutate again and everything will go kaput again.
Yes, correct. Because it's really random value happening. And okay, any other opinion on why we keep it low as we can?
My thoughts on this is because the GA is basically inspired by how humans evolve. So as we can see, humans evolve very slowly, very gradually. So if we put the mutation probability too high, it will be almost all the gene will be changed in one generation, which is not really logical if you think of it from a biological perspective.
Correct. It's not really inheritance anymore. It doesn't happen. And one more point is, it's similar point like both of you saying just now. Most probably you will get the best solution by luck because mutation because you change the chromosome randomly with random value from outside. So if you get the best solution, is it really from the population? Is it really the population got evolved, or you got it by random chance, by lucky mutation? Okay, so we don't want that. We want the algorithm to evolve based on whatever it has. From time to time, we can choose mutation probability to be executed, but not as high as crossover operation. So in this case, we always set to 0.1. Okay, I change it to 0.1. And let's run it again and see what happened. What do you think will happen when we change it to the low probability?
Probably children and parents will be the same.
Probably whatever we have as the result as crossover. won't change. Okay, mutation is not happening. Wait, I will share my black screen. Okay, now my black screen here. Let's say if we mutation did not happen for both children. So whatever we have in crossover, the children is still intact. And these children will go to the next process, which is survivor selection. In survivor selection, we will select whether we want the children or we want the original parents to be brought forward to the next generation. Okay. Okay. This is about mutation. And another thing, this is an example of you only change one gene. Okay, if you have long chromosome, you might want to consider to change several genes. But again, set the mutation probability low, so you don't change the structure too much. Okay, that's all for this lab. Any question?
No.
This is about the previous lab. So, in the tournament part, so we have the fitness of player one. If it's less than player two, then player one wins. But the thing is, we have negative fitness as well. So if it's negative 20, it's still smaller than 0.1. But in our problem, we want it to be as close as possible to 0 rather than as small as possible.
Ashraf, we don't have negative fitness value. Yeah, we don't have because we absolute it.
Okay, so it's my code. Okay.
Okay. You shouldn't have negative value. The way we normalize the fitness value, we should have 0 to 1 and only.
Okay.
Correct your fitness formula.
Mhm.
Okay, any other question?
No.
Okay. Mutation is pretty straightforward. The process after this tu yang saya rasa I really need your understanding to understand how survival selection happened and how we brought this into the next generation. That's important. And if you can see right now in our main, we don't have any loop yet. Okay, but actually crossover and mutation will be looping as well as the survival selection. It will looping from one generation to another generation to another generation. So starting from next lab, I hope you can see the whole GA. Rather up until this lab kita tengok the process individually. Crossover macam mana, mutation macam mana, evaluate crossover macam mana, we still look at it individually. That's why I didn't include the next week lab into the lab test. Lab test, you just need to study on chromosome representation, parent selection, crossover, and mutation, all the individual process. Okay? For your lab test, you need to understand the concept and the strategy and your code as well. Starting next week, we are going to wrapping it up. We're going to combine everything and look into the next generation, what will happen in next generation, and that's require your understanding as a whole GA rather than single function only. Okay, itu kita tunggu next week. So I don't want to combine this week punya lab with survival selection. Let's settle with our lab test first. After lab test, then we continue with survival selection and wrapping up the GA. Wrapping up the GA, we will look into what is the average fitness value of our population, whether this generation is better from last generation, or what is the best chromosome in this generation compared to the next generation, and so on. So we need to do some graph on that, okay, for wrapping up the GA. Up until this point, code ni still straightforward, individual process only. Okay. Any other question before I end this lab?